you these pictures. So this is the first continuity homework that I kind of needed help with.
Okay.
Okay, one second.
You still
Okay.
have my email?
Yeah. Let me just send you these problems.
Attach them as files so that I can
yeah.
load them up or shrink them if I need to.
Okay.
If you're using an Apple iPhone,
should be sending.
Attach them as large image files.
Oh, okay. Usually I do actual size, but I'll do large from now on.
Actual works also. The only thing that doesn't work is small size.
Okay.
Small size.
And then I'll send you.
Yeah, either actual or large image
I'll send
attachment.
Okay. So I'm going to send you a bunch of problems that I needed help with because, so we also learned intermediate value theorem. And then we also, that was mainly it for.
Whose theorem?
Sorry, what?
You mentioned a theorem, I think?
Oh, yeah, intermediate value theorem.
Oh, the intermediate value theorem. Okay.
Yeah. Okay.
Got your pictures. Here, let me. Okay. Want me to start from the left?
Yes.
I think. Okay.
Sorry, one second. And then I'm also going to send you another email of a bunch of the problems that I need help with. Most of these involve trig because trig is not like my strong suit. So yeah.
Okay, that's fine. Trig is, it's probably more important in Calc BC, but it kind of depends on what the trig problems are. All right, let me take a look at this one right here.
Okay. Yeah, so this is the first one that I didn't know how to do. This is the first one I didn't know how to do. It was cosecant 8x. I know it's a non-removable discontinuity because if you look at the cosecant graph, there's a asymptote at like a set value. So it's a non-removable discontinuity. But I don't know how to get the x values where the f is not continuous.
All right. Well, let's examine the function. Okay? That's the first thing we want to do, is examine that. Where is that undefined? Where is cosecant undefined?
Yeah, that's the thing. I kind of forgot the domain and range of cosecant, secant. I think I need to review that.
The easy way to remember this is, first of all, what's the reciprocal of cosecant?
Sine.
Okay. Where is sine equal to 0? Because wherever sine is equal to 0, then the cosecant's going to be division by 0, which is undefined.
Okay, so it's usually equal to pi, 2 pi, 3 pi, like that.
Yeah, it's 0, pi,
yeah,
or 2 pi. In other words, multiples of pi. That's where sine is equal to 0.
Yeah.
Which means that's where cosecant
is
undefined.
No, yeah.
Okay.
So where it's not continuous.
Exactly. Now, so 8x has to be those.
Oh, the period is 2 pi over 8, which would be pi over 4.
Yeah, but it's 8x that can't be equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi.
Yeah.
So forth. So x is going to be equal to 0 over 8, pi over 8, pi over 4, 3 pi would be 3 pi over 8, pi over 2, and so forth and so on. I don't know that they listed a domain here as to how far up we should go, but we'll start there.
Okay.
Okay, now, Find the x values at which f is not continuous. Okay, well, we did that.
Yeah. So would it just
I
be
don't see
0?
the rest of the question. Which of the discontinuities? I don't.
Oh, hold on. Let me see what it said. 1 second. Hold on, just 1 second. Sorry, I usually try to take it. Okay. Oh, past assignments. Okay. Yeah. So yeah, it says which of the discontinuities are removable. So that's just asking whether it's removable or non-removable.
Well, yeah, the terminology here for discontinuities. You have jump discontinuities, non-removable, infinite discontinuities. This is actually going to be an infinite discontinuity. I mean, if I plot the cosecant, it sits on top. The easiest way I find to plot the cosecant is to put it on top of the sine curve. Here, let me.
Oh yeah. Okay.
Let me use a different color. In other words, this is the cosecant curve. On the top
but the thing is,
and
for some reason, so is my answer incorrect?
I don't know what your answer is.
Oh, I put it in there. X equals pi over 16 plus pi over 8. Okay.
Oh, well, are you talking about this?
Yeah, that was my answer, but they said
that
it was
was
wrong.
your answer. Okay. Okay, so k is the multiples of pi over 8.
Yeah.
So how about when k is 0, then x is pi over 16?
Well, that wouldn't make sense. It should have just been pi over 8k, right?
Well, if I look for all the x's that are undefined, I get 0. That's
Pi over 8.
Well, that's not pi over 8.
Oh.
If k is 0, you end up with pi over 16, not 0.
Yeah, so would it just be no pi over 16 instead? I would just get pi over 8k.
Yes. Pi over 8k covers this one when k is 0, covers that one when k is 1, covers that one when k is 2, covers that one when k is 3, and so forth and so on. So, yeah, that's the correct answer. Pi over 8k.
Okay. Okay. So I just tried another version just as you and I were speaking. I tried another version where it was cosecant 9x, and this time I put in my answer as pi over 9k, and that's correct. So that makes sense. Okay. That makes a lot of sense. So to recap really quickly, the values where k is discontinuous. Okay, that would just be all the values where cosecant x is not continuous divided by the coefficient.
Well, it's if I draw asymptotes on this curve, I've got an asymptote every pi over 8.
Yeah.
That's where it's not continuous. It's not continuous there. It's not continuous there.
Yeah.
So it is not continuous at all of these asymptotes going in both directions. So you have to cover that one, and you have to cover minus pi over 8. But this does. In other words, k can be a negative 1,
negative integer, yeah.
Be a negative 2, and so forth and so on. So yeah, if it's cosecant of 9x, then it's just all of these divided by 9.
9, yeah. So that one, now that makes sense. Okay. And then I needed help on the remaining problems in that. There's a couple more, I think. Yeah.
On this page or on the next page?
Oh, no. Yeah, on the next page. Yeah, I didn't know how to do both of these.
Okay. Let's look at 12. Okay. If you don't know how to do these, kind of a good way to look at them is to graph them. And then you can actually see where it's discontinuous.
Yeah.
Okay. Well,
Okay.
minus 9x is a slope like this.
Yeah.
Line, that's linear.
Mm-hmm.
And x squared minus 8x plus 5 is a parabola that must look something like that. I may not have drawn it in the right.
Negative p over 2a. So it's usually, so I think it's the x value is 4 and 4 comma something would be the vertex.
Okay.
Yeah.
Well, oh, I see. When x is greater than 2.
Oh, right. So yeah, so obviously it would be discontinuous at 2. That makes sense. And it's a non-removable discontinuity because it's not a hole that you can just plug in with a point.
Okay, yeah, let me redraw my graph here. I didn't draw it very good. In other words, I didn't look at the domain as I was drawing it. So I definitely want a parabola, but it's only a parabola to the right of 2. So if I put a 2 there, then the parabola is like this,
Mm-hmm.
something like that. Okay?
Yeah.
Now, find the value at which f is not continuous.
Yeah, that makes sense that it would be 2 because
It's going to have to be 2 because,
exactly,
yeah, there's no other. If I look at this graph here, I don't really see a discontinuity other than, here again, let me, there. Now I've drawn it correctly.
Mm-hmm.
And here, hold on. In other words, this is really what it looks like.
Yeah. And then it would make sense that this is non-removable because it's not just one hole in the graph where you can plug it in with a point.
Exactly.
Rather, it's like a larger.
Removables look like this.
Yeah. Mm-hmm.
That's a removable discontinuity.
Mm-hmm.
This is not. You cannot do anything to this graph that gets rid of that discontinuity. Whereas over here, is all you got to do is drop that down to there. I guess that's one way to look at it. But yeah, so, okay, so that was the correct answer.
And then I don't know how to do number 13.
Okay, have a look at it. Consider the following. When the absolute value of x is less than 1, well, let's try to draw this one. Let's see. What's that equal to when x is 1?
Tan pi over 4, which would be 1.
Okay. So when x is 1, that's equal to 1. And we know the tangent curve looks kind of like this. And then it's equal to x alone when x is greater than 1.
But then it says, okay, but this is absolute value x. So wait, what's the difference?
Well, that's a good question. Hold on, let me draw it.
Okay.
So that's kind of what the curve looks like.
Mm-hmm.
And of course, I can erase this part of it.
Oh, right. It makes sense that there's no discontinuity.
I don't see a discontinuity there.
Yeah. Mm-hmm. Because it's at 1, 1, and the graph of x will pass through 1, 1 as well.
Right. And in fact, that's not a discontinuity.
Yeah.
By the definition that I gave you. In other words, if I examine that point, the limit from the left is this point, the limit from the right is that point, and the value at 1 is that point. Now, the fact that it says absolute value
Mm-hmm.
Well, let's see. When the
Does that mean it only
absolute
goes towards 0?
value, that means if x is negative, let me think about that for a moment. When the absolute value of x is 1, so I think this is going to look something like this. In other words, usually absolute values have a v.
Yeah, yeah.
Well, that's as close to a v that I can draw,
Mm-hmm.
I think. Let's see. When x is less than 1, let's say when, hold on a second. So let's examine when x is less than 1, the absolute value, which is this area right here.
Mm-hmm.
When x is negative, in other words. When x is negative and less than 1, then it would be this function, the tangent function. Gosh, I think that looks the same thing, doesn't it?
Yeah.
And then if x is negative but greater than 1, which means like negative 2, it's a straight line. So with a slope of 1.
Mm-hmm.
So,
But either way, it would be the same thing where there's no discontinuities and it's there's no discontinuity, so none of them are removable either.
well, were both those answers correct?
But yeah, if you see down there, it says x equals none, NA no discontinuity, and there's a check next to it.
Oh,
So that means
that means
yeah.
it's correct. Okay. Yeah, I don't see, well, hold on a second. I don't see discontinuities there, but what about if x is 0? If x is 0, that is this function, which is the tangent of 0, which is 0. So actually the tangent crosses through there
Mm-hmm.
in both cases. So yeah, it's going to look something like that with no discontinuities in it. Yeah, I don't know why I drew it this way. I was trying to kind of draw the reverse or the mirror image, and that's not what it is. You actually have to go through, the way to do these problems is to substitute some numbers.
Mm-hmm.
In other words, this is the case whenever it's between -1 and 1, correct?
Mm-hmm.
So between -1 and 1, you have the tangent of pi times the x over 4. So, and tangent is 0 at 0. So between -1 and 1, if I label that -1 and I label this 1,
Mm-hmm.
it's going to look something like that. There's no discontinuities there.
Yeah. Mm-hmm. I
And
see.
whenever it's greater than 1, which means everywhere to there and everywhere to there,
Mm-hmm.
it's a straight line. So you do end up with this picture that I drew, which is
Yeah.
that, that, and that.
Yes, I see it.
Okay?
Okay. So I need help on the next problem as well.
Okay. On the third page.
Mm-hmm. Yeah.
Okay.
So the first one is the 4x, number 11. It's near the bottom. 4x minus cosine x.
Okay.
So how would I know what the graph of this looks like? 4x minus cosine x.
All right, let me think about this for a second. Where is it not continuous? Well, you would need an asymptote, probably, to be not continuous. How do you graph 4x minus cosine x? Are you allowed to use a calculator on this?
No.
Okay. Let's, hold on a second, just a second. Because these combinations of trig functions and polynomials, which is what this is,
Mm-hmm.
those are tough to graph if you have to do it by hand.
Mm-hmm.
I can kind of give you an idea of how to do it. The most, usually when I get problems like this, people are allowed to use their calculators so you can put it in. Well, that's 4x.
Mm-hmm.
This is cosine of x.
Mm-hmm.
Now, if we're subtracting the blue line from the red line,
Mm-hmm.
then obviously, let me use a different color here, green. For this point right there, it's clearly right there.
Mm-hmm.
Red line minus blue line. Over here, it's positive. Over here, it's more positive.
Mm-hmm.
When it gets down to here, it's exactly this point right there. When it gets,
I don't understand how you're graphing this. Like, how are you subtracting it?
well, by the values of f of x. In other words,
Oh.
assuming, I'm not sure, yeah, I drew my graphs correctly, I think.
Mm-hmm.
Okay, if you want to know what 4x minus cosine x is, well, what is it right there?
Um, 0.
Minus 1,
But
which is negative
yeah.
1. Okay, so
Okay. Okay.
that's where that point would lie.
Okay. Okay.
If I'm graphing it right there, where they're the same, then that's going to be 0.
Mm-hmm.
So that's how I'm doing it.
Mm-hmm.
Now, just to be clear, let me introduce you to another program. Have you ever been on Wolfram Alpha?
Yeah, I've seen it before. They have a bunch of widgets that are like,
Oh, it is
uh,
great. It is a
mm-hmm.
terrific math site. It's called a computational knowledge database,
Mm-hmm.
but it really is a math site. Okay? And
Mm-hmm.
I'm going to graph 4x minus cosine x just to show you what that graph looks like.
Mm-hmm.
Now, it's going to graph the results, okay? And if we go back to, well, I'm not sure I can get back to it. No, I can't get back to it. Unfortunately, when I write on these pages and I close it out, I can't go back to it.
Mm-hmm.
But it's kind of, it's not quite what I drew. First of all, when x is 0, how is this not minus 1?
I think it is actually. So I graphed it on Desmos.
Oh,
Just
it is. Yeah, it just doesn't,
yeah, it is
it
0
doesn't
comma
look
next
like
one.
minus.
Yeah, so you were right. It's
Yeah,
0 comma
the
next.
scale is the scale is screwed.
Mm-hmm. Yeah.
We're just not expanded very much. But that's the way you're going to graph it, is you're going to graph 4x, you're going to graph cosine x, and you're going to subtract. In other words, you're going to go from left to right on the x-axis
Mm-hmm.
and just subtract the two values and plot that point, and then connect the dots. Okay?
Mm-hmm.
And we can see from this graph that there are no points of discontinuity.
Mm-hmm.
Not at least between minus 6.3 and plus 6.3. And those numbers are key. What is 6.3? That's 2 pi.
Okay.
Basically 2 pi. If you think of pi as being 3.14, then 2 pi is 6.3. So their domain on this graph is minus 2 pi to plus 2 pi.
Mm-hmm.
And anything beyond that probably isn't going to change much. In other words, cosine x is continuous the whole way. 4x is continuous the whole way.
Mm-hmm.
So it would be hard to imagine subtracting a continuous function from another continuous function,
Mm-hmm.
not getting a continuous function. You almost would have to.
You might hold it for just a quick second so I could get my notes and I could see, because I feel like my teacher might have said something similar, like for function, if there are two functions, like there are two types of functions, like 4x and cosine x, and they're both continuous, then the entire function is continuous.
Right. Now, if this was tangent x, then there are going to be places on tangent x that are not continuous.
Discontinuous, yeah.
In other words, every pi tangent x is not continuous. It has a vertical asymptote. Whenever you have a vertical asymptote, that destroys continuity.
Mm-hmm. But so let's just say I had 4x minus tangent x, like they said to give me that on the test.
Okay.
How would I approach that problem?
Well, let's try to draw that.
Okay.
And I'm going to use 3 colors. I'm going to graph the tangent x, I'm going to graph the 4x, and then I'm going to use a third color. So let's start with my regular color, and that's going to be 4x. You agree that that's a pretty good 4x?
Yeah.
Okay. Now I'm going to graph tangent x in blue.
Mm-hmm.
Now, tangent x goes from minus pi over 2 to plus pi over 2.
Mm-hmm.
And it has asymptotes. Whoops, got to draw it through the origin. So it kind of looks like this. Now, since the red line goes forever, both directions, then the vertical asymptote that would be right there is not discontinuous because there's a red point. Well, hold on. I was going to do this the way, I'm going to do this the way that we're supposed to do it. I forgot to do that, which is to subtract the blue line from the red line. In other words, this is tangent right here. So if I take the red line, which is 4x, and try to subtract tangent, well, that tangent goes to infinity. So 4x is a number, minus infinity is still going to be infinity. In other words, that is going to have vertical asymptotes. Every place that there is a vertical asymptote on tangent of x.
Got it. So there would be pi over 2, pi over 2, sorry, pi over 2.
It would be pi over 2 plus k pi.
So 3 pi over 2, 4 pi, 5 pi over 2,
Uh-huh.
7 pi over 2, 9 pi over
Yeah,
2, like,
these vertical asymptotes are exactly right.
okay,
They come every pi.
okay.
In other
Um,
words, the period of tangent is pi. It's not 2 pi like the period of sine and cosine.
mhm.
Plus sine and
Okay.
cosine have no points of discontinuity.
Mhm.
So yeah, if you're subtracting a continuous function from another continuous function, I find it difficult to believe that there would be any points of discontinuity. I can't
Mhm.
imagine one because you're always going to have a number.
Yeah, that makes sense.
Whereas with tangent or cosecant or secant, those all have vertical asymptotes or
Mhm.
cotangent. All four of those have vertical asymptotes. So
Mhm.
wherever you have a vertical asymptote, you're going to have a discontinuity because a number minus infinity or minus a negative infinity is going to be discontinuous at that point, regardless of what the number is.
Mhm. Okay. So, I see what you're saying. So for the next problem that's like right on top of number 11, um, so yeah, and if you go
Roll
to,
up? No. No, hold on. I'm in Wolfram Alpha.
oh, okay, okay, okay.
Let me get out of this. Uh, you're talking about f of x equals 3 over 9 minus x squared?
Yeah. So for this one, would I just do 3 over, well, this is a difference of two squares, so it would be 3 minus x and 3 plus x.
Exactly. In other words, what you're looking for is where this thing is undefined.
Mm-hmm. And
Only
I think the thing with,
undefined when x is minus 3 or plus 3. It's
mm-hmm.
only two spots.
And also, I think my teacher said something about how like if it was on the in like a rational function at least, if it's like on the bottom, then it's a this if there's like a zero in the bottom, then it's a asymptote, and if it's on the top, it's a whole.
Well, if it's on the top, it's not necessarily a hole. Here, let me give you an example of a hole. Hold on. This would represent a hole because that becomes x minus 1,
And x plus one.
x plus 1. The
Oh,
x
right, anything
minus
can
1's
cancel out.
cancel out, but
Right, right,
there's still a hole at x equal 1.
one. Okay, okay, okay.
In other
Got it.
words, just because we factored and canceled it doesn't
Hmm.
change the fact that x can never be equal to 1.
Yeah.
Even though this reduces to x plus 1 and x being 1 doesn't appear to be a problem here, but it is. In other words, just because you can cancel them out does not take away the domain restriction.
Hmm.
X can never be 1, and when x can never be 1, that means vertical asymptote, that means non-removable discontinuity.
Right. Okay. That makes sense. Okay, so then those would be so it would be -3 and 3. And since they don't cancel out, they would be asymptotes, vertical asymptotes, and they would so which a vertical asymptote is a discontinuity that is non-removable.
Exactly.
Okay.
I
All
think
right. So
the only discontinuities that are removable
mhm.
are ones that look like this. I believe. In other words, anytime there's a vertical asymptote, it's definitely not a removable discontinuity.
Right, right.
The
Hmm.
only reason that's removable is because if I take that point away, then the thing is basically continuous. It's not
Yeah.
really because there's a hole there, and that hole means that it's not continuous. So
Uh-huh.
whenever you have a hole, you do have a discontinuity. In other words, this function right here would definitely be discontinuous at x equal 1, wherever
Yeah.
there's a hole. It would be a removable discontinuity,
Continuity. Okay.
but that's the only thing.
Yeah. Okay.
I believe
So
that's
then,
the main difference between removable. I think there's three kinds of discontinuities. You have infinite, which is when you have vertical asymptotes. You have removable, which is when you have this situation.
a whole.
And non-removable is when you have this situation. In other words, a piecewise function where I can't remove it.
Right. Okay. So for us, the way they taught it, they didn't say infinite per se. The way they taught it was like the non-removables both include the scenario that you just described, and they also include vertical asymptotes.
Okay. All right. Yeah. The terminology is different depending on what school you go to. And I've always had a little bit of difficulty with their terminology because everybody uses different terms. But yeah, that's basically it.
Okay.
I
And then there's
suppose you could call a removable discontinuity where that's the only removable kind I can think of, where I could almost draw the function without lifting my pencil, but not really.
Yeah.
In other words, if I remove that point and make that point down here, then it's a removable discontinuity. I guess that's where they came up with the name. I'm not sure why they even have names for it, to be honest with you. There's really only three kinds of discontinuities that I can think about. I guess they're deserving of names. So, all right. Should we go to the next page?
Yes.
Which is this fourth one here, I think.
Mm-hmm. I think there's 3 pictures. Yeah, there's 3 pictures on that one. I needed help with all of them, really.
Okay. Ooh, weird stuff. Hold on. For some reason, every time I clicked on it, all of a sudden it starts rotating.
Sometimes it does that.
Weird.
Yeah.
Weird.
Yeah.
Let me see if I can get around that by downloading it instead of just displaying it.
Mm-hmm. I can try to verbalize it though. It's not too.
Yeah, it's not. I think I can actually read it. Unfortunately, now that. Yeah, let me see if I can. Yeah, let me look at it without expanding it. What are we looking at? Number 6.
Yeah, and number 6, 7, and 8. Those are the 3.
Okay. Notice what number 6 looks like.
It looks like a normal. It looks like a. I forgot.
Looks like f of x plus delta x minus f of x all over delta x as delta x goes to 0 from the right.
Mm-hmm.
So that is the definition of first
derivative. Oh, right.
In other words, that right there, usually they use h's, although I noticed that both times we've talked about it, they tend to use delta x in your class as opposed to h. But notice if f of x was 9 over x, then f of x plus delta x is 9 over x plus delta x.
Mm-hmm.
So what we're looking at here is that's f of x. Excuse me, that is f of x plus delta x. That is f of x. There's a delta x.
Yeah.
So is all we have to do is we can either do the math on this or we can just use our, they haven't taught you the power rule yet?
No.
That's criminal. It really is.
I think they
you
try
have
to make
to do this the hard way, the algebra way.
Yeah.
But I'm going to continue to just teach you the power rule because it'll speed some stuff up for you. Correct? That's what f of x is? Mm-hmm. What's f prime of x?
Wait, hold on one second. How did you get f of x is? Oh, right. That makes sense. Okay, okay. 9
In other
over x.
words, whenever you're dealing with derivatives, you don't really want your variable to be in the denominator.
Mm-hmm.
So I turned it into the numerator.
Right. That makes sense.
Now
Yeah.
I can use the power rule. So it's
Okay.
minus 9 times x to the minus 2.
Oh, wait, sorry. Can you explain the power rule to me really quickly one more time?
Yeah. The power rule is the best way to explain it is if y equals nx to the k,
Mm-hmm.
then y prime is equal to k times n x to the k minus 1.
Okay. That makes sense. So it would, in
That's
this case,
always
be
the case,
9
no
times.
matter what
Yeah.
k is, no matter what n is.
Mm-hmm. So it would be 9 times -1, which is -9, and then -1 minus 1, which is -2, which would just be -9 over x squared, which is the
Which
correct answer.
is that.
Okay, perfect. So if we could just speed through the next
Now,
few problems, 'cause I have a
let's
couple
just
other
talk
problems.
about one other thing.
Mhm.
This isn't exactly the definition of first derivative because they've got it approaching zero from the right only.
Uh-huh.
But that's not really going to matter. I don't know why they put that approaching zero from the right only. They could have
Yeah.
left that off,
Mm-hmm.
and that's still the answer, minus 9 over x squared.
Mm-hmm.
The reason they ask you this problem, I mean, you could do the algebra.
Right.
You got to find a common denominator.
Dominator. Yeah.
When you do the algebra and cancel what you can cancel, you're going to end up with minus 9 over x squared.
Mm-hmm.
It's just much easier to get there using the power rule.
Yeah.
Okay? Trust
Yeah.
me, the moment they teach you the power rule is the last time you'll ever do it this way.
Yeah. So
But,
I needed help on
but
these
they're going to
next.
ask you questions that show you that format, and you have to recognize that as, wow, that is the first derivative of 9 over x.
Oh, okay. Yeah,
In
that
other
makes
words,
sense.
you have
Okay.
to know that this part is f of x plus h. This part is f of x. So I've got f of x plus h minus f of x all over
Mm-hmm.
h as h
Yeah.
goes to 0. That's the
Okay.
official definition of first derivative. Since we
Mm-hmm.
know the first derivative of that is minus 9 over x squared, then we can use the power rule to come up with it, and we don't have to do all the algebra. I can do the algebra. You want to go through the algebra on this?
It's okay because I actually have a couple other questions that I needed, and I emailed you those as well. So, which is why I want to like go through these really quickly too.
Okay. So the next one below it, number 7,
Mm-hmm.
find the limit if it exists.
6 cotangent x. I forgot how to. I think you need to know the graphs of the
All right.
trig function for these.
Well, tangent does this.
Yeah, and there's an asymptote at pi over 2, right?
Cotangent is the reflection about the y-axis of that, but it doesn't
Okay.
go from minus pi over 2 to pi over 2. It goes
Uh-huh.
from 0 to pi.
Okay.
Okay, so
Okay.
if I draw the cotangent curve, it looks like this.
Mm-hmm. Okay.
And that's kind of the way you can tell them apart, because if somebody said which curve is, in other words, cotangent looks a lot like negative tangent, right?
Mm-hmm.
If
Yeah.
you had the negative tangent curve, it
Mm-hmm.
would actually look just like this,
Mm-hmm.
parallel to my cotangent curve, but not in the right spot. The negative tangent curve goes from minus pi over 2 to plus pi over 2, whereas the positive cotangent curve goes from 0 to pi and then repeats. In other words, it has a vertical asymptote every pi.
Right.
Okay?
Okay. And
So,
so the limit would not exist because.
what
Right.
as
The
time
the
goes
right side limit
by,
goes towards infinity, and the left side limit goes towards negative infinity, so it does not exist.
exactly.
Okay.
The left side goes to negative infinity, the right side goes to positive infinity. Since they're not the same, the limit at pi does not exist.
Okay. What about number 8? Secant x.
Okay, again, the best way, well, I don't know. I mean, everybody has their own way of doing things. The
So
two
usually you
curves,
could just
the two
draw
curves
the.
I know how to draw for sure are sine and cosine
Yeah.
and tangent.
Yeah. Those are the ones that I know too.
Okay. Well, cotangent, excuse me, we're looking at number 8.
Secant. So opposite of cosine.
So it's the reciprocal of cosine.
Uh-huh.
Cosine looks like this.
Yeah.
So the reciprocal of cosine is going to be undefined whenever cosine is 0.
So at
We have a
pi.
asymptote there. We're going to have an asymptote. Let's see, that's actually pi over 2.
2, right.
And that's 3 pi over 2.
So it would be pi for sine though, right?
Yes.
Okay.
Well, it's wherever sine is 0. And sine
Yeah,
is
so that would be
0
pi.
at 0, at pi, and at 2
Pi.
pi. So
Okay.
sine is 0 every pi, but cosine is 0
Every pi over 2.
over 2
Okay.
plus k pi.
Mm-hmm.
So if we're looking for where at pi over 2, that's going to be undefined. In other words, that at pi over 2 is where cosine is 0. And if cosine is 0, then secant of pi over 2 is infinity.
Right.
In other words, here's what, let me draw the the secant curves.
Okay.
The secant fits on top of the peaks and on bottom of the valleys.
Mm-hmm.
So I know that there's going to be a vertical asymptote and going to infinity there.
Right.
And I know on the other side, as we approach pi over 2, we're
infinity.
going to negative infinity. Therefore, it does not exist.
Okay. So that makes sense. I understand those two. I sent you another email with a bunch of pictures, and this is also more about continuities,
Okay.
I think. But it was just like a little bit harder, and I didn't really get the trig part of it.
Must be this email here.
Yeah.
Starting with the first one. Okay. Find all values that f is continuous on. Find all values of c such that f is continuous on that interval. Well, what usually you have to end up doing on problems like this, if you're trying to force continuity, that means at c, this function has to be the same as the bottom one. In other words, we have two piecewise functions here.
Mm-hmm.
So however these graph, I need that to equal that.
Okay, so you would set 9 minus x squared equal to x?
Yep, 9 minus x squared equals x, which gives you x squared plus x minus 9 equals 0.
Mm-hmm. Oh, and this one you can't factor, so you would use quadratic formula.
And that's why we get answers that look like that.
Right. Okay.
Okay, so you plug it into the quadratic formula, you get two answers, plus or minus, and that's how you do it. In other words, this is the key part of the problem right there. As long as you can do that as your first step, you're always going to get this right.
Yeah.
And that would be because one of them's a parabola and one of them's a straight line. The bottom one looks like this, but the top one looks like a parabola where something like this. It's upside down.
Oh, okay, okay.
And where we want are where those two are equal.
Okay, so the intersection point.
Yeah, because notice what it looks like. If C is right there, then I have something that looks like that. And in other words, I can draw that without lifting my pen.
Right, okay.
But more importantly, like I said, the mathematical definition is the limit at that point right there from the left is that, the limit from the right is that, and f of c is that. Those are the three things that have to be true for something to be continuous.
Mm-hmm.
If all three of those are not true, then it's not continuous. Notice that if we had the one I keep drawing, the limit from the left is the same as the limit from the right, but the value at that point is not the same as both of those limits. So that is not continuous. All right, next page.
Yeah.
The Signum function. Wow, I've never heard that term.
Me neither.
Wow, that really is funny. It looks a little bit like a greatest integer function.
Yeah, that's what I thought.
Okay. It's not quite the greatest integer function, but find the following if possible. The limit of this as x approaches 0 from the left is what?
Oh, that's okay. This one is pretty easy. I don't know why
Yeah, it's minus 1.
Yeah.
From the right, it's plus 1.
Yeah, and then it does not exist because
Does
the
not
limit
exist because they're not the same. So
okay, yeah, next one.
this, I don't seem to have a picture on the, oh yes I do. Okay.
Yeah, so I didn't know how to do number 6. Not number 5, but number 6.
Number 6, okay. Again, let's draw the secant function. And we'll even do it with secant is opposite of cosine, therefore it's going to look something like this. Not opposite, but in other words, I've finally gotten to a point where I can draw the secant without drawing the cosine.
Right.
And in fact, I didn't. Yeah, I said I could do it, but I didn't. That goes like this. Okay?
Yeah.
Now, what does the secant of pi over 4 times x look like?
Okay, so I think for this one, you would do 2 pi over 4, which is equal to 8. So the period would be 8. So one half of the cosine like curve would be 4. It would be between the values 0 and 4. So it would be continuous from -2 to 2 because each of them have to be 4. The distance between the two numbers have to be 4 and 2 and 6.
Here we're seeing a distance of 4 between all of those.
Okay, so that one makes sense. I kind of get that.
Yeah.
And then number 5, how would I know that?
Figuring out the period. Now,
Yeah.
let's talk about trig for a moment.
Yeah.
The period is for everything but tangent and cotangent is 2 pi over b.
Right.
With, in this case, b is pi over 4. That is the coefficient of x, correct?
Right.
Okay, so if b is pi over 4, you're right, the period is 8, which means it's 8 from there to there, which means it's 4 from there to there.
Yeah. That makes sense.
So it's going to be discontinuous every 4. It's going to run into a vertical asymptote. And it's definitely, you can almost answer this by process of elimination.
Right.
That can't be right. That's not, those aren't separated by 4. Those aren't separated by 4. That's not.
Definitely
And
not
those are.
negative infinity to
So there's
infinity.
only one answer there where they're all separated by 4.
Yeah.
So really, this is a pure trig question.
Yeah.
All you have to really know is this, that the period is 2 pi over b, and b is the coefficient of x, which is pi over 4. Plug it in, you know what the period is. Half of the period is where every half period you're going to have a discontinuity.
Mm-hmm. Okay, so then, yeah, so that makes sense. Can we go to the next page? Because that's one of the last questions I had.
Okay, hold on. This one right here.
Yeah.
Okay.
Yeah, I need help on number 7 and 8. It was intermediate value theorem, and I don't really understand how to do that.
Well, let me describe what the intermediate value theorem is.
I remember actually. Okay, I do know. So, if there's a value a, if there's a point a comma b, and sorry, a comma f of a, and there's a point b comma f of b, there must be between those two, every x value between those two points
As
will have a
long as
corresponding
it's continuous, it has to be continuous.
Mm-hmm.
In other words, intermediate value theorem only applies to continuous functions.
Mm-hmm.
If this function is piecewise,
Mm-hmm.
then the intermediate value theorem doesn't apply.
Right.
But as long as it's continuous, no matter how it goes, it can
Mm-hmm.
go like the following. That's
Yeah.
continuous. And what the intermediate value theorem says is if you have a continuous function, then all values between a and b have to exist. You can't get from a to b without going through every value between a and b. Kind of a way to look at the intermediate value theorem, the best example I've ever heard is you can't go from 10 miles an hour to 50 miles an hour without going through 20,
Every single,
21, 22, 22 and a half. You can't go straight from 10 miles an hour to 50 miles an hour. You can't jump. No matter how much acceleration you have, you can't do it. You have to go through all values in between. All right, so now let's see if we can answer this question. Looks like you've answered it okay. You got it correct. So if I plug in 2, find the value of C.
Oh, I think what I would do is I would set 13 equal to c squared plus 4c plus 1, and then I would get 13 minus 1, which is 12. And 12 is equal to x times x plus 4. And that's, or no. I would do minus 30. So it would be x squared plus 4c plus 12. Sorry, minus 12. Right, and then I would factor and get
Which
30.
is x minus 2 times x plus 6, right?
Mm-hmm. And then you would get x equals 2 or x equals negative 6. But you can't do negative 6 because that's not in the interval 0 to 1.
Okay, I was just going to say, how come we don't have a negative 6 answer? And that's because of that right there. In other words, the interval is from 0 to 5 inclusive.
Mm-hmm.
So negative 6 is not in that interval.
Yeah.
All right.
And then so the same applies to number 8 as well.
Yeah, let me look at 8. Yeah, you just set this equal to 6.
Yeah.
Solve it. You might get two answers. Choose the answer that's in that interval. Which you did. Looks like it's 3. You don't have any problem with the algebra solving that?
Yeah, no, I don't. That makes sense. I understand this.
Okay.
All right. So I think I think I'm good for today.
Okay.
All right. I'm gonna see the rest of the syllabus, and if I do need help, I just need to set if I want a session tomorrow, I need to just book it 2 hours in advance, right?
Yeah, or call me. You know,
Okay.
if you only have, I think only 1 hour is the way I've got it set up.
Okay, perfect.
If it
I'm
has 2 hours, call me, and
okay.
I can make time. I
Okay.
don't have a lot going on tomorrow, so I'll be able to make time
Okay.
any time.
Yeah. I
But
might need a little help just because I do understand it, but not exactly. Like I really want to work on. I need somebody to help me with like practice problems for limits at infinity. So like when x is approaching infinity,
mhm.
I need help with that. So I will ask my mom to book a session tonight. It's
Okay.
not a problem.
Yeah. No,
Yeah.
I understand those problems pretty good, so I can help you with that.
Okay, perfect.
Um,
Yeah, so I'll
no,
just check
I
in.
am curious on your last test. I'm assuming there were no epsilon delta questions?
No, there weren't. And my teacher said they don't even do that in Calc BC in our school, so we
No,
don't need
they
to
don't.
worry.
That's why
Yeah.
I was going to say it's not. That's why Saul Kahn said that it is not, should not be part of an introductory calculus class.
Yeah.
It's way too advanced for an introductory calculus class.
Yeah.
And you're going to run into a similar thing when you get to integral calculus, is they have a pure mathematical definition of it.
Hmm.
It's harder than nails to understand. I've worked through it a number of times, but just like the epsilon delta thing, I only get presented about once every 5 years by a student with that problem. So
Hmm.
I tend to forget it after 5 years. So if you come across that, give me some heads up. I'll
Hmm.
review it and I'll be able to help you with it. But those are the
Okay.
only two things I can think of in calculus,
Mhm.
and neither one of them are going to be on your AP exam.
Yeah.
You'll have to know
I also really
that.
quickly wanted to
Teachers
let you,
don't do students a service by even introducing them to it.
yeah. Mhm.
It's
I also
demoralizing.
wanted to let you know something else. So basically, my next unit so this Friday and Tuesday we have a test on the this work. Sorry, the limits chapter. The next chapter is differentiation. So the first one is derivative and tangent line. That's the first section. The second section is basic differentiation rules and rates of change. Third section is product and quotient rules and higher order derivatives. The fourth section is the chain rule. The fifth section is implicit differentiation, and the sixth section is related rates.
All of those are easy except related rates.
Okay. Okay. Cool.
But you do have to learn them in order. You can't do
Okay.
related rates unless you know how to do implicit differentiation.
All
But
right.
implicit differentiation is easy. Power rule, product rule, quotient rule, and chain rule are easy. You just have to memorize what they are.
Yeah. Okay.
But they're easy to apply. Much,
Okay.
much easier than the limit quotient definition, which is f of x plus h minus f of x all over h. You won't ever use that again, except maybe on a final. You might have to know that for your AP exam, that limit definition.
Limit quotient. Okay.
Yeah, but that really just comes down to difficult algebra.
Hmm.
No matter what the function is, if you apply that, f of x plus h minus f of x, then you just
Hmm.
have an algebra problem.
Hmm.
So, um,
Yeah. And then so our chapters are like so basically there's first we had differentiation and then there's application of differentiations and then integration. I think that's integrals. And then logarithmic, exponential and other transcendental functions. Then we have differential equations, applications of integration, integration techniques and improper integrals, infinite series, and then conics, parametric equations, and polar coordinates, which I'm definitely going to have a lot of trouble
okay,
with
infinite
because
series and everything you said after that, is Calc BC. That's not Calc AB.
Ooh, that's in our textbook.
Okay, well, I can do infinite series. I've done infinite series with people, but
Okay.
only Calc BC students. I've never done infinite series with a Calc AB student.
Oh wow.
And
Okay,
in
well,
fact, improper integrals is not a Calc AB subject either. But we'll get to those whenever you get to them. So you're
mhm.
supposed to cover all of that within this first semester, or
Not within the first semester. I think okay, so starting with infinite series and onwards, that's second semester. But just before first semester, we're going to be doing all the way up till improper integral.
okay, all right, that's good to know for me. I don't. I might have to. The infinite series is really some tough stuff. It really is.
Yeah.
We'll talk
So,
about that when we get there. We
yeah.
don't talk about that until we get there. All the other stuff, fairly straightforward. As I said with calculus, they tend to give you the hardest thing first.
Yeah.
And that's exactly what your teacher did. He gave you the epsilon delta definition, which is absolutely the hardest part of differential calculus. And then he gave you the limit quotient definition, which is the second hardest part of.
Yeah.
I don't know why they teach calculus that way. It's not necessary. When I teach calculus to somebody without a syllabus, I never do it that way.
So actually
Power
for us,
rule, the product rule, the quotient rule, the chain rule.
mhm. And for us at least, what was I gonna say? So they usually, I mean, I it's just our school, like they do this in honors pre-calc as well. They give like a really, really hard test on the prerequisites chapter. They give that so that to like kids who aren't like ready for like the rigorous.
That's the reason, because you know what? You brought up a good point. Every math subject is like that. When you took geometry 2 or 3 years ago, they start out with proofs. That's the
Mhm.
hardest
Yeah.
part of geometry.
Yeah.
When you take algebra 2, they start off with linear programming. That's the hardest part of algebra 2.
Yeah.
And when they start off with trig, they start off with radians and degrees, and that's the hardest part of trig.
Yeah.
Math seems to go that way. They like starting every math subject off with the hardest part of that subject.
hmm
And maybe it is for the reason you said, to weed out the people that don't belong in that subject. I'm
So
not
yeah,
sure it really does that, especially with calculus. I mean,
I'll
expecting
also.
somebody to understand the epsilon delta,
Mhm.
that is not necessary to be proficient
Sure.
in calculus. You can get an A plus in calculus and not have a clue how to do any of those problems.
Yeah. I got kind of scared when I saw those symbols.
Hmm.
Yeah. But
I tell you
anyway,
what, if you do want an excellent explanation of the epsilon delta, just go to Khan Academy, and type in, do a search for epsilon delta definition. And
was
he has a little 10-minute video that is great. I
okay.
actually had to use it myself to try to understand it.
Okay. Okay. All right. Thank you so much, Mr. Cohen.
You're welcome.
All
Talk to
right.
you next time, Srini. Bye-bye.
Yes. Bye.